Thank you, Thierry. Thank you to the organizers for inviting me. So I will talk today about, yes, a new technique, namely dynamic nuclear polarization, and I will show you what can be done in the frame of apatites, substituted apatites, and also kidney stones, so natural samples. I have to, first of all, say thank you to my colleagues, namely César Leroy, who is doing his PhD on this topic, Thierry Azaïs, Florence Babonneau, and many thanks to Dominique Bazin and Michel Dodon, because they introduced me to this special topic of pathological calcifications, namely kidney stones. And also we have collaborations with colleagues in Japan, as well as with Geoffrey Bodenhausen, Marc Caporini, and Fabien Osnac for the development of these DNP techniques. So as you probably know, and I think that the talk by Thierry this morning, the talk by Etienne just now, they have shown you that solid-state NMR is now a crucial technique for the characterization in material science. You can study biosolids, namely big proteins. You can ask the question about polymorphism, for instance, in the case of pharmaceutical samples, hybrid materials involving, organic, inorganic interfaces, nanomaterial, biological materials such as diatoms, and there is a very nice poster by Sylvie Mas and Guillaume Laurent. And I think that the key point is, yes, it tells you what the structure is, but it gives you also a lot of information about dynamics. This is why I think solid-state NMR is so interesting, and Thierry has shown you this morning that you can not only have the fingerprints of the nuclei corresponding to the chemical environments, but you can also have very fruitful insight into the dynamics of the systems. So there is only one drawback in NMR, and this is a big one. If I take this sentence by Goodson, the sensitivity of conventional NMR techniques is fundamentally, so it's physics, is fundamentally limited by low spin polarization. In other words, in NMR you have no signal, or almost no signal. So what I want to show you in 20 minutes is that you can manipulate the system. You can fight a little bit in terms of preparation of the sample, instrumentation, and also how to treat, mathematically speaking, the signal. And I chose here, these are the topics we are all developing currently in the lab, but I will focus today on small coils. First of all, why is it interesting to use small coils? And secondly, the major part of the talk will be devoted to DNP. So, imagine a tooth of a mouse. So this is the size of the tooth, roughly, and it corresponds roughly to 1 milligram of sample. If you put this 1 milligram of sample in a big rotor, let's say a 4 millimeter or 7 millimeter rotor, you will have no signal. Doesn't mean that you have no spins. You have a lot of phosphorus, and you have all 31, and also a lot of protons, because we are dealing mainly with apatite, let's say biological apatite. If you take exactly the same sample, put it in a very, very small coil, so 1.3 millimeter, that's the size of the rotor. So the rotor is very, very small. You work at very high field in order to increase the sensitivity and spin very fast at the magic angle. You can record a 2D experiment in a very reasonable amount of time, namely here 3 hours. And Thierry this morning showed you a lot of these 2D maps. So you have here horizontally the phosphorus dimension. Here you have the proton dimension, and the correlation peaks tells you what are the spin, the protons talking in terms of dipolar interaction to the corresponding phosphorus. So this corresponds to a classical 2D map of related to hydroxyapatite, but it's obtained here with a very, very small sample. Why does it work with a very, very small coil? Because in this case, you increase the filling factor of the coil, and so you favor the transmission of the RF signal, either the emission and also the reception of the NMR signal. So that's why you have very beautiful results in terms of sensitivity, in terms of signal-to-noise ratio, by using these very, very small coils. So I switch now to DNP. And what I want to show you, and I think that's a recurrent topic here in this audience, that's the problem of appetite. This is the architecture of a stoichiometric appetite. You recognize here the OH groups corresponding to the A sites, and also the phosphate groups here corresponding to the B sites. And in this talk, I will present you some results related to substituted appetite, namely by carbonates and by silicates. And from the cationic point of view, I will choose sodium. Okay, so what are the challenges in the case of substituted appetite? The problem is that, first of all, we have to deal with the large variety of substitution. But in this case, solid-state NMR is the good answer, because you can tune the Larmor frequency, and it's a local probe, and you can check carbon-13, you can check proton, phosphorus, silicon-29. That's a good point for us. What is not good in terms of sensitivity is the fact that all the substituents are all present in limited weight persons. Namely, it's below 5 to, let's say, 5 to 7 weight person, first of all. Secondly, we are dealing here with carbon-13 when we are working in natural abundance, or silicon-29, and we know that these are spin 1/2, but with they are low abundant nuclei. You probably know that the natural abundance of carbon-13 is 1.1% and 4.8% for silicon-29. So in terms of spins in the sample, which are active when considering the magnetic field, it's a very, very small portion. So you will, as I told you, the sensitivity is directly related to the number of spins. So here, intrinsically, we are dealing with a very low number of spins. Much more complicated. If we are looking at calcium-43, magnesium-25, which is very important also in substituted appetites, then we are dealing with spins which are strictly higher than 1/2. In this case, we talk about quadrupolar nuclei. I don't go into the detail. The problem is that in this case, even if we are spinning very fast at the magic angle, you will have a residual broadening, making the sensitivity less and less. And finally, all these nuclei are usually low gamma. What does it mean? It means that as the sensitivity is related to the cube of gamma, the sensitivity is decreasing and decreasing and decreasing. So the answer could be do infrared, and it will be much, much faster. So I take an example. If you have here a sample with appetite with silicate inside, what we decided to do several years ago with Florence Babonneau, who is in the audience, was to make a true transfer from protons. There is a sequence called cross-polarization, enabling us to make a transfer from the protons coming only from the OH groups of the columns to the silicates, which are here. And so what we have to do is first of all to filter the proton magnetization. So we keep the proton magnetization of the OH groups here alive, and the proton magnetization corresponding to water, for instance, is dying due to this spin lock block here. And then we make the transfer from proton to silicon, and the detection here under decoupling from the protons is on the silicon-29 channel. So, result, a very good one, because here we extracted very nicely the silicates which are inside the structure corresponding to the Q0 units. Why Q0? Because the chemical shift, which is minus 72 ppm roughly, is clearly related to Q0 species. The bad news is that we worked at that time with a full 7mm rotor. So it means 300 to 350 milligrams of samples, and after 2 days, we had this miserable signal-to-noise ratio of about 5. The info is okay, the info is present, and 2 days is a weekend, so in a sense it's not a big problem. But is it possible to improve the signal-to-noise ratio? If you need 2 days to have 1D, one spectrum, 1D, one spectrum, it means that if you want to do a 2D, you have to add many 1D spectra, and then you multiply 2 days by, let's say, 32 or 64, and you see the experimental time you need. So it's hopeless. So, DNP. DNP was invented here in Paris by Anatole Abragan in the 50s, and it's a sort of extension of the Overhauser effect, which is one of the key experiments ever invented in nuclear magnetic resonance. And due to all the work by Bob Griffin at MIT, it's now possible to do DNP at high frequency. What does it mean? It means that if you are able to put some spies, and the spies are electrons, so radicals, if you put spies in your material and you irradiate the electronic transition, so that's pure EPR, so you irradiate the electrons, then that's a theory, and that's beautiful, that's magic of this experiment, you have a strong transfer of polarization from the electrons to the nuclei. That's a pure Overhauser effect. And you see the difference. That's a work done in 2010 by Emsley and co-workers in Lyon, in France. And you see here the spectrum. That's a carbon-13 spectrum without the DNP effect, so almost nothing, let's say in a given amount of time. As soon as you have this DNP effect, so the microwave, MW for microwave is on, you have a huge increase in signal-to-noise ratio. So what we decided, so that's the apparatus, the DNP equipment. So that's first of all an NMR spectrometer. So you recognize here a big magnet, 10 Tesla, roughly. So it's 400 megahertz for the proton. So it means that you need a 280 gigahertz on the EPR side. And then so the power, the microwave with high power is produced by a gyrotron. And so you have here a little cartoon of what happens. In fact, you have a totapole, for instance, a biradical. You irradiate the EPR transition of the electrons, and then by this hyperfine couplings and cross effect or Overhauser effect, you will boost significantly by orders of magnitude. I will show you the results soon. The nuclear polarization of proton, and then remember the CP experiment I presented you between proton and silicon-29. As you have now a huge amount of magnetization here on proton, you can transfer it in a second step by a cross-polarization process to the silicon-29, carbon-13, and so on. So does it work? This is the first sample I tried rather recently with carbonates. So this is 1% in weight in carbon. This is a hydroxyapatite. And what we can see, if you look carefully at the black curve corresponds to no DNP effect. The microwave is off. As soon as you open the microwave, the microwave is on, you see that you have a huge amount of signal corresponding to the phosphorus, carbon, and also proton magnetization. So for all three nuclei which are interesting here, proton, phosphorus, and carbon-13, you have almost an epsilon factor, so an enhancement factor of roughly 23. So 23, what does it mean? You can prove mathematically, more or less, that the gain in time is the square of epsilon. If you take the square of epsilon equals 23, then you have a gain in time of more than 500. So you see now NMR is not more unsensitive technique. It becomes more and more to be a very sensitive technique under DNP conditions. What does it mean? As I told you, if you can record very fast a 1D experiment, which is the case here, and depending on the sample, depending also on the biradical, I have shown you the totapole radical, which is here, but you can use also the amupole radical, then the epsilon can increase from 23 to 42. Again, if you take the square of 42, it means now almost 2,000 in gain in experimental time. That's crazy in a sense. What does it mean? It means that you take minutes, only minutes, to get very nice spectra. This is a carbon-13 spectra corresponding to this carbonated apatite. You recognize here the A sites, and Etienne showed very nicely the A site, the B sites, and so on. You still have the resolution, even if it's at low temperature, etc., with a solvent, with totapole, with amupole, and so on. And as you get this kind of spectra within minutes, then it's very, very fast also to get 2D experiments. Here I'll show you a triple resonance experiment, proton to phosphorus to carbon-13. So you end up with an experiment correlating the phosphorus of the structure and the carbon-13, and then you can play with the interpretation of the correlation peaks. Something I'm quite, I think it's a nice one. That's the question, where are the carbonates in the structure? A site, B site, or AB? The possibility to have close to an A site, a B site. It has been predicted a long time ago by Delieu and in 2005, 2006. And in fact, due to this enhancement in signal-to-noise ratio, it was possible to record a two-dimensional experiment involving carbon and carbon. So what does it mean? It means A site here present two peaks, and if you take this horizontal line, the A site is obviously correlated to what is a B site. You have here a B site which is autocorrelated to himself. You have also this B site prime correlated to another site. So in other words, as you have no correlation peak corresponding to AA, you have no clustering of the carbonate ions within the columns. So as soon as you have an A site, you have a B site which is close, very close in space. I cheated a little bit because here, in order to have enough signal-to-noise ratio, I used a labeled sample. So it's 1 weight % in carbon, but 100% in carbon-13. So the next question is it possible to extend all these experiments to natural sample, I mean to natural abundance samples? So this is exactly the same. This is a carbonate, 1%. Natural abundance, as I told you, 1.1%, and you see that in 10 minutes you have a very nice spectrum. And it would take, on a standard experiment, let's say, more than 20 hours to get something like this with the same volume of sample. And as soon as you have a 1D spectrum, again, in 10 minutes, it's possible to record very fast 2-dimensional experiments, 2 double resonance, and even triple resonance experiments. So that's not big deal now. The last example I want to show you in this topic was in fact the first obtained by Florence and myself. I come back to the problem of silicates in apatites. Remember this spectrum, the Q0 spectrum obtained after 2 days of experimentation. Here you see that without microwave you have nothing after 12 minutes for sure, but by using the microwave and the DNP effect, after 12 minutes you have a very nice spectrum corresponding to the Q0 units at roughly minus 72 ppm. And now you know what to do. If you have a nice spectrum in 10 minutes, you can do a nice 2D experiment. That's a silicon proton experiment, and it was the interpretation of the correlation peaks are in good agreement with what was predicted by colleagues in Clermont-Ferrand, Nedelec, Gomez, and so on. The last few slides are related to natural samples. So here I want to thank again Michel Dodon and Dominique Bazin. We are working a lot with César Leroy on this topic. Carbon NMR is very nice, for instance, to make the distinction between the calcium oxalates, depending on the number of water molecules. Here, this is the one water molecules, 2 water molecules, 3 water molecules. It's possible also to record calcium NMR spectra, which are very sensitive to the local environment of calcium in this case. But what about DNP? So we tried, we took a sample of a kidney stone, and you see here that it works perfectly. This is the microwave off, so it's standard NMR, let's say in 2 minutes or things like this. Here, the microwave is on, and you see the gain in the signal-to-noise ratio. We were really happy, but this spectrum corresponds to the protein. So because the kidney stone is complex, it's a protein and also a large amount of calcium oxalate, here monohydrate. And the problem is that if we look very carefully at this region, corresponding to the carbonyl groups of the proteins, but also to the carbonates within the structure. The carbonates also, by the way, but also oxalates. You see here that we are strongly underestimating the peaks corresponding to the oxalate. They are here for sure, but if you take a standard NMR spectrum, carbon-13 NMR spectrum of this particular sample, you will have you will have 3 very big peaks corresponding to a large amount of oxalates. So it means that in the case of heterogeneous materials, there is a lot to do. If we want to use DNP for this kind of sample, we have to think about the impregnation technique, the solvent, the effects of the solvents regarding the surfaces, the interfaces. So I think it's completely open, but we have a very nice effect on the protein part for sure. But we have to still work in order to establish by NMR the connections between the minerals and the proteins. So that's the end of the work, of the talk, and I think that the next future could be to apply the DNP experiment to calcium and magnesium. Remember, these are very, very complicated nuclei. For instance, calcium-43 is 0.14% natural abundance, so it's nothing. It's a quadrupolar nucleus, so here we need signal. And I give you an example obtained with Daniel Laurencin a few years ago. You see here after one full day, 7 millimeter rotor, so a lot of sample. We have this, yes, nice spectra, yeah, because I'm spectroscopist, so that's very nice. I can make a deconvolution and so on, but it's clearly hopeless to do more, and it's in particular, it's impossible to do 2D experiments in this case. And to finish, we are working a lot with these people in Grenoble, Gaël de Pape, Daniel Lee, and Frédéric, in order to implement these techniques. And listening to the talk by Etienne, I was thinking about sulfur-33, which is also a disaster in NMR because it's low abundant and so on. But as you are in sulfates, it's a very symmetrical environment, and maybe the line would be sharp, and DNB could be an option. Thank you.